Hello, IB. We're looking at 14b, limits at infinity. So in 14a, we were taking the limits as we approached a certain number. So now what happens as we go toward infinity? Um, Remember that infinity is not a number. We are going closer and closer to infinity, but we can't define it as an actual one location. But we are going to go get closer and closer and closer. So whatever function we decide to choose, and we're going to start just by looking at x and x squared because they are very familiar to us. So if I graphed y equals x squared, or sorry, y equals x, I start with just a linear function through the origin with a gradient of 1. What we're looking at here, again, we're familiar with this notation, the limit of our function x as x approaches infinity. So as x goes toward infinity, so x is going to get larger and larger and larger, we look to the right for x to go to infinity. So if we are going to look to the right, what we're trying to follow is what's happening to our y value as we look to the right. So if I take my points along this line and I go toward the right, I'm actually going to the right, but I'm also going up at the same time. So remember, right is our x direction. When we look up, that's our y direction. So we're saying as x gets larger, my f of x, or my y value, is going to be going up, and it's going to get larger and larger and larger toward infinity. So we actually do not have a limit here because our f of x is going to be approaching infinity. So therefore, we just say that the limit does not exist because f of x is going to infinity. We can also shorten that. You might see dne does not exist. So let's see what happens for our limit of our function x as x goes to negative infinity. So again, this time I'm following my graph to the left as my x value is going to negative infinity. So what's happening to my y values? As I look to the left, my graph is also going down, which means that my y values are approaching negative infinity. So again, our limit does not exist because our f of x is approaching negative infinity here. So let's see what happens with x squared. If we have our graph x squared and x is approaching infinity, I'm going to look to the right. So as I look to the right, my y values are increasing, and they're increasing much faster because now I'm taking all my x values and squaring them to get my y values. So I'm still approaching infinity as I was with my linear graph, but I'm getting there a lot faster. So I'm moving in that direction a lot quicker. But remember, it's not a location, or it's not a specific location or number. So we still have the limit does not exist. I'm just going to put quotes there. And that's because our y value is going to infinity. I'm just writing this down as a note so we remember what we're looking at. All right, so then what happens to our graph, or to our function as we look to the left? So as x approaches negative infinity, where's our f of x going? And it's also going to infinity, so we can say it does not exist as well for the same reason. So all in all, if we change these functions, they're polynomials. So if we have any kind of polynomial here, as our power increases, we're just going to increase toward infinity or negative infinity faster and faster and faster. So remember, if we have an even degree, we've got two ends of our graph that are going in the same direction, whereas if we have an odd degree, like x, or x cubed would be our next one, you have one end of your graph going to a positive direction, one to a negative direction. So you're still approaching infinity. So this whole idea of a limit would not exist as we are always approaching positive or negative infinity. So let's see if we can look at a different style of graph and analyze that one with the same idea. So now we're looking at our rational functions here. We wind up having, let's just look at 1 over x as our first function. Okay, our hyperbolic function, 1 over x, we have a vertical and a horizontal asymptote. So we have a vertical asymptote at x equals 0, horizontal asymptote at y equals 0, and we're familiar with this graph because we've worked with it several times. We know how to find a vertical asymptote by setting our denominator equal to 0, but we've never quite defined how we get that horizontal asymptote. So now let's take a look at what happens when we look at this graph as x approaches positive infinity. So 1 over x is graphed. We're taking the limit of our function 1 over x as x gets closer to infinity. So again, I'm looking to the right. And if I look to the right, what is happening to my y values as I continue to look to the right? So my y values are going to get smaller and smaller and smaller and smaller and smaller until we approach 0. Again, by definition of an asymptote, I'm never going to wind up hitting 0, but I'm going to get so close that I can say I approach 0. If I look to the left, the limit as x approaches negative infinity, so I'm going to look this direction. What is happening to my y value as I look to the left? So my y value is going to get smaller and smaller and smaller, and it's also going to approach 0, but from the other side. So on the right, I approach 0 from the top, from the positive y value side, and on the left, I'm approaching 0 from the bottom, or the negative. So again, as x approaches negative infinity, I still approach 0. So now let's take a look. What would happen if I start with x over x squared? So a different function to begin with. Well, we've been simplifying. So the limit as x goes to infinity. Let's go ahead and try to simplify this, because x over x squared means I really have, I've got 1 over x. That's really being multiplied by x over x. Okay, common factor. So x over x, I can cancel out. We've just been discussing how we get wholes. So I'm really looking at just 1 over x again. All right, so the limit as x approaches infinity of 1 over x. Remember, this denominator here tells me I get a vertical asymptote, and then I would also have similar horizontal asymptote, but I have this additional whole piece. So what we've just been discussing is that as you look at your graph toward the right and to the left, so as x goes to positive infinity and as x goes to negative infinity, you actually wind up finding your horizontal asymptote. So by definition, your horizontal asymptote is the limit of your function as your x value approaches negative and positive infinity. So we're just going to write that out together. So by definition, your horizontal asymptote is the limit as x approaches positive and negative infinity of whatever your function is. Okay? There are certain functions where different things will happen to the graph around 0. So remember, we want to make sure that we are always looking at our function as x approaches infinity and negative infinity to really look at where our asymptotes are. So just going through this one example here, example 2, discuss the behavior of the function 2 minus x divided by 1 plus x near its asymptotes and try to deduce their equations. So we're actually going to start by looking at the graph. We did spend some time in year 10 graphing these, and then again in year 11 at the beginning of the year, graphing rational functions. So we've got our vertical asymptote, we know is when your denominator is equal to 0. So I can go ahead and set 1 plus x equal to 0 and realize that my vertical asymptote occurs at negative 1. And then we just had a discussion about looking at your limits of your function as x goes to positive and negative infinity. So let's take a look and see. I'm going to go to our graph here. Oops. So this is the function. And if I wind up following my function to infinity, so I'm going to take a point here and I'm going to continue moving it to the right. We notice that our x values are getting larger and they'll continue to get larger. Notice what's happening to the y values. So my y value is at negative 0.8 right now, and it's going to continue to get smaller and smaller and smaller. And let's see if I can follow it out to the left to negative infinity. Notice my y value is at negative 1.4, and it's getting higher, negative 1.3, negative 1.2. So let's see if I can zoom out a little bit. See what happens when I really go to the left here. Negative 1.1, and if I continue to go, negative 1.04. So we're getting closer and closer and closer to negative 1 as your x goes to negative infinity. Let's see what happens as x goes to positive infinity. Also, y value is getting closer and closer to negative 1. So we can say that our horizontal asymptote is going to occur at -1, when y equals -1. The question also asks us to look at what's happening around the vertical asymptote. So if I approach my vertical asymptote, notice your y value is approaching -infinity. It's getting smaller and smaller and smaller if we're coming from the left direction. If I'm coming from the right direction and I approach -1, where my vertical asymptote is, then your y value is going to get closer and closer to positive infinity. So let's write that up formally. Part A was asking us to discuss the behavior as we get closer to the asymptotes, so the vertical and the horizontal asymptotes. So as x goes to -1 from the left direction, so as I approach -1 from the left, we were saying that your f of x is going to approach -infinity. So if I come from the left, I'm going to go down toward -infinity. As we approach -1 from the right, so if I'm coming from the right and I approach my vertical asymptote, then your f of x is going to approach positive infinity. So let's also take a look at the horizontal asymptotes, which means as x is approaching -infinity, so when I looked to the left, your f of x was approaching -1. So when I was looking out to the left, we were getting closer and closer to -1. And also as x is approaching positive infinity, so when we were looking out to the right, my y value is also approaching -1, just from the other direction. So in part B, it says state the values of the limit as x approaches -infinity and positive infinity if they exist, and they did. And that was my horizontal asymptote. So we can say the horizontal asymptote occurs at y equals -1. So we've taken a look at how to analyze and find the your horizontal asymptote from a graph. However, how would we do that algebraically? So thinking back to how we originally started this, we wanted to simplify the function, just like when you guys were first, a couple days ago when you're first working with limits. So you want to wind up simplifying the function that you're working with so you can analyze it appropriately. So here, I'm going to go ahead and set up my definition of a horizontal asymptote by using limits. So I'm going to say my limit as x approaches infinity, and again, we're thinking positive and negative infinity here, of my function, 2 minus x over 1 plus x. In order to reduce it down to actually analyze it, I'm going to divide the numerator and denominator of the fraction by the highest power of x. So my highest power of x in this problem is x. These match. They both are a power of 1. So I'm going to divide through each of the terms. So I'm going to take the limit as x approaches infinity of 2 over x minus x over x divided by 1 over x and then plus x over x. So I've just taken that x value, the x term, because that is the highest degree, and I've divided all 4 terms in my problem by x. What's going to wind up happening is I'm looking at the limit as x approaches infinity. The x over x reduces, so I have 2 over x minus 1, and I have 1 over x plus 1. And if I take the limit as x approaches infinity, so if x gets larger and larger and larger and larger and larger, then this whole fraction is going to wind up going toward 0. Because your denominator is going to get so large that 2 divided by a really, really large number is going to get so small that we can say it's going to approach 0. So 2 divided by x will go to 0. The same will happen for 1 over x. 1 divided by a very, very increasingly large number will also go to 0. So then we are left with -1 and 1, which means therefore our limit would be -1. So we can say that this function would have a horizontal asymptote at -1. So horizontal asymptote when y equals -1. This is the appropriate way to lay out your work and to show how you actually get that horizontal asymptote. I do want to show you guys one little hint. When you look back up to the function, notice that as you divide through by the highest power, you're always going to be left with whatever the coefficient of those x terms, or whatever that x term actually is. So my coefficient for x is -1. Coefficient for this x is +1. So -1 divided by +1, I will wind up getting -1 as my horizontal asymptote, because the constant terms will wind up going toward 0. If we use that same thought process in this question, again, notice that our highest x term is x squared, and they also match. So if they match, again, we would be looking at the coefficients. So I'm going to guess that my horizontal asymptote is going to occur at 1/3. And I'd like you guys to set up this question and see if you can prove that the limit actually does wind up being 1/3. So my horizontal asymptote winds up being 1/3. All right. So this one we are going to leave for you to try. And to start our discussion next class, think about what would happen if your terms did not wind up matching. So let's say I divided through by the highest degree, which in this example would be the x cubed. So what happens if I divide all 3 terms here by x cubed, and then I take the limit as x approaches infinity? So set both of these up and see if you guys can kind of analyze what's going to happen to the limit. Have a great night. Have a think about this, and we'll continue chatting next time.